All right, good morning. I'm Captain Bruce Shea. I'm the commanding officer of the Pacific Missile Range Facility. We're the Navy's premier training and test and evaluation range, and we're hosting NASA for a program called the Low Density Supersonic Decelerator. If you're watching this, you probably already know what that is, so I'm not going to waste any time explaining it because it's pretty awesome and pretty complex. The reason we're here at Kauai and at the Pacific Missile Range Facility is because we have a lot of space. If you're not familiar with our range, we have 2.1 million square miles of extended range complex. And although the balloon's not going very fast, it is going to use up a lot of real estate, and especially in altitude. So in order for us to launch it safely and then recover it safely and track it, it seemed like the logical place. We've also supported NASA stuff here in the past. And I know I'm personally very excited about watching this thing take off, go active, and then do all of its things it has to do before it goes in the water. And I'm even more excited about the possibility of getting to test the follow-on concepts here at the Pacific Missile Range Facility. We're really happy to be partnering here with NASA and JPL and all the other folks that are out here for, well, you've been here for months now, it seems like, so you're almost Kama'aina. I don't have a lot more to say except I'm, again, super happy to be sharing our range with our friends from NASA and showcasing the fantastic people we have here at the Pacific Missile Range Facility. Thank you.
Thanks for that welcome, Captain Hay. I'm Dave Steets from NASA Headquarters Office of Communications, and I want to welcome everybody as well, our friends in the media who are here today. I'd also like to introduce the rest of our panel. In addition to Captain Hay, we have Dr. Michael Gazarek. Mike's the Associate Administrator for Space Technology at NASA headquarters in Washington. To Mike's left, we have Ian Clark. Ian is the Principal Investigator for the Low Density Supersonic Decelerator, and Ian's based at NASA's Jet Propulsion Lab in Pasadena, California. And next to Ian is Dr. Mark Adler. Mark's the program manager for the Low Density Supersonic Decelerator, or LDSD. Mark's also with NASA's Jet Propulsion Lab in Pasadena. We'll hear some opening remarks from Mike, Ian, and Mark, and then we'll take questions from folks here in the audience, and then we'll also take questions from reporters joining us on the telephone. You can also ask questions via our hashtag AskNASA. If you're following us on Twitter, we'll be entertaining questions from the public on hashtag AskNASA during the briefing. And with that, I'll turn it over to Dr. Gazarek. Mike?
Thanks, Dave. And thanks, Captain Hay. I really appreciate your hospitality for allowing us to be here for months. I don't know what we promised you. We will leave, though, eventually. But I want to really thank your team for hosting us here for this important and exciting test. This test kicks off really 3 months of increased focus by NASA on the importance of technology to achieve our ambitious future science and robotic missions, and eventually human missions to Mars. So before Mark and Ian kind of take you through the details, let me just step back a little bit and talk to you about why it's so important to invest in technologies. In order to go to an asteroid or go to the moon or go to Mars, we need sustained and substantial investments in space technology. Without these investments, we really can't go beyond the International Space Station, where we have crew there today. Technology drives exploration. And in fact, technology is the surest path to Mars. The Space Technology Mission Directorate, a little over a year old now and running, is responsible for a lion's share of the technology development, which is critical, again, for exploration above the low Earth orbit. We continue in the Directorate to look at a variety of technologies and also to engage the best and the brightest in the nation. We have connections and programs that involve academia. We have now over 450 activities with over 120 U.S. institutions, and all working on the tough, difficult problems we have at NASA for space exploration and for the broader aerospace community. All the while doing these investments, we're making improvements and gains in the American economy, in the innovation economy. We're looking at high priority challenges as we move forward in exploration. In fact, we have 7 launches in the Space Tech Mission Directorate in the next 24 months. That's 7 launches plus what we're going to do here tomorrow in the next 2 years. The investments span a broad variety of areas, and I'll talk about that in just a minute. But they are important for us, and they are important for the nation to explore. Just last week, the agency introduced what we call the Evolvable Mars Campaign. It's a series of steps to lead to pioneer to Mars, not just explore, but pioneer. And technology is certainly one of those steps. And in fact, as Charlie Bolden, the NASA administrator, had said, and the President's science advisor, Dr. John Holdren, technology development is the surest path to Mars. When we look at Mars, we've been there before. 8 successful landings on the surface of Mars. The United States leads this area in landing on Mars. It's one of the more difficult challenges, and clearly the Jet Propulsion Laboratory and these two gentlemen here to my left know a lot about that. When we look at the Curiosity rover, which landed a year ago or 2 years ago, it's about a metric ton on the surface of Mars. We know that for exploration, for future robotic exploration, for future human exploration, we need more than that. And how do we do that? And that's what we're about here today. We have been living really on the shoulders of the giants who developed the entry, descent, and landing technology decades ago. In fact, there's a picture of it now from the Viking era back in the 1960s and 70s. And so for us, it's the challenges of Mars. How do we get there? How do we land there? How do we live there? How do we leave there? And today, and the event we're talking about focuses on that very difficult challenge of landing there. We know this, we need to test and we need to learn, and we need to do it quickly and efficiently, and that's, again, why we're here. The specifics of the deceleration technologies we're going to talk about, again, we'll leave to the experts here, but it will enable more mass to the surface. It's about more mass going to more elevations on the surface of Mars and landing more accurately. EDL is actually one of many technical challenges to get to Mars. And in the next 18 months, the Space Tech Mission Directorate has a number of substantial investments in a broad number of areas. Let me just highlight a few. In addition to the entry, descent, and landing technology we're talking about here, also the idea of getting there, propulsion. High-power solar electric propulsion. We have a substantial investment in this area that has broad applicability. For NASA, the first step for us is moving beyond the low Earth orbit of the International Space Station and going and retrieving an asteroid and bringing it to the Earth-Moon space. We call this the Asteroid Retrieval Mission. In that mission, with a robotic spacecraft, we will use high-power solar electric propulsion. This technology not only can help move asteroids, but also can serve as cargo vehicles to get to Mars and has broad applicability for our nation's commercial spacecraft. It has a number of applications. It's a multiple win, not only for NASA, but for the nation. Likewise, we have investments in robotics and avionics. Spirit and Opportunity, the rovers on Mars, covered 10 kilometers in about 10 years. We're trying to work on technologies that can do 10 kilometers in a week. And how do we do that? We know we need advances in avionics and robotics and sensing. We're also looking at optical communications and the ability to send pictures and high-definition data back. Materials and structures, of course, remain a key component for any type of exploration. So these are the areas we invest in. We know from previous history, it is about risk. We need to address risk, and certainly the testing we're doing here has some risk in it. But we need to take and address the risk today in these kinds of tests to reduce the risk for missions for Mars tomorrow. And that's why we're here, testing and learning as fast as we can. So regardless of the outcome, we know we will learn many important things. We'll learn many important things about this technology, and again, this is the first step. We'll be back next year. Hope you knew that. We'll be back next year, right, for future testing. So with that, let me turn it over to Dr. Ian Clark, the incredible PI of this effort. He is the EDL, he's the architect behind what you're about to see. Ian?
Thank you, Mike, and thank you everybody for attending. Personally, this is an extremely exciting time for me, and I really enjoy the juxtaposition of here we are in one of the greenest and lushest places that I've ever been, testing technologies to eventually enable much broader, more capable missions to land on the surface of Mars, a planet that has beauty in a number of other ways. And so we're here because 4 decades ago, the Viking landers, were some of the first missions to land on another planet. The United States and the world, for that matter, was learning what it means to land spacecraft on another planet. And the technologies that were developed over 4 decades ago are some of the same technologies that we still rely on today to land our spacecraft on Mars. And one of the remnants of that technology development program, if you go to the next image here, this was some of the testing that was done as a precursor to the Viking program At the time, they were trying to develop supersonic parachutes that would enable them to decelerate the Viking spacecraft to land on the surface of Mars. And we've been using that same parachute for several decades now. And as we start looking towards the horizon and want to land more capable missions on the surface of Mars, heavier to higher altitudes, with more relevant science associated with them, and land them more accurately, and as we want to land eventually humans on the surface of Mars, we realize that we need to develop new technologies that will enable us to do that. And the technologies that we're testing here, two new technologies associated with the Mars program, are a supersonic inflatable aerodynamic decelerator. You can go to the next image. Thank you. It's the image on the left is a SIAD, supersonic inflatable aerodynamic decelerator. This is an inflatable torus or drag ring that we inflate at several times the speed of sound to provide more drag to slow the vehicle down as it enters the Martian atmosphere. And then the technology on the right is a new supersonic parachute, something significantly larger than any parachute that's ever been tested or flown supersonically in the past, and will enable us to grow the landed mass capability on the surface of Mars by at least twice, and we think it's extensible to something even more beyond that. Go to the next slide. Thank you. So some of the testing that we've had to do to develop these technologies, there's a lot of questions that we have associated with these. How do they deploy? How do they inflate? They're going to be strong enough to survive the extreme environments of Mars. How are they going to behave aerodynamically? What is the performance of these devices? And some of the testing that we've already done on these is to answer the question is, are they strong enough to survive? And so to answer that, we started developing new test capabilities. We would have loved to have tested these in wind tunnels, but unfortunately there are no wind tunnels in the world that are big enough to test the size of devices that we need to test and the conditions we need to test. And so we've started developing new ways to do that. Something that NASA hasn't had to do for several decades. But again, this is an exciting time, and as we start thinking about trying to do even more capable missions on Mars, issues that we have to wrestle with is how do you do those tests? And so one of those was working with our Navy colleagues at the China Lake Naval Air Weapons Station. We started coming up with an idea of using a rocket sled. It's a 20-foot tall siege tower, if you will, that we accelerate to several hundred miles an hour in a fraction, a few seconds. And what we do is we inflate, actually if you could go back to the previous video, please. Thank you. We accelerate this sled at several hundred miles an hour in a few seconds, and we use that to replicate the aerodynamic loading that some of our technologies will see, in particular the supersonic inflatable aerodynamic decelerator. So the images that you're seeing are, this first one is a shakeout test of that, and now you're going to see it inflate. This is actually a slow motion video. The inflation of the side occurred over about 0.2 seconds, a fraction of a second. And all the testing that we've done to date shows that these devices work extremely well. Very exciting for sure. But what we have to do is test them to make sure that they're going to be strong enough. And associated with the side, we have the new parachute. You can go to the next video on that. We had to develop new ways of doing the parachute testing to make sure that it was going to be structurally strong enough. And so the video that you're seeing is similarly using a rocket sled. And there's a little bit of an ingenious idea here. Again, working with our colleagues at the Naval Air Weapons Station at China Lake, where we used a helicopter to take the parachute up to several thousand feet altitude, where it was released, dropped and inflated, and you see it inflating now. And there's a long rope that goes several thousand feet down to the ground, wraps around the pulley. You see the rope passing around that pulley, and then we light a rocket sled that would accelerate horizontally down a track and pull the parachute towards the ground. And we could generate over 100,000 pounds of force to make sure that the parachute was going to be structurally strong enough to survive the environments that it would see if we were to use it at Mars. And that's just some of the testing that we would do in preparation for a Mars mission. And then Mark is going to talk a little bit about some of the testing that we're doing here in addition to that.
All right, good morning. I'm going to talk about what we're actually doing here out in Kauai. Tomorrow is our first launch opportunity for getting this balloon and test vehicle launched. I'll talk to you about exactly how that all works. We have opportunities over the next 2 weeks dependent on the winds and the weather. This is our first experimental test flight of this vehicle that is designed to carry the side and the parachute that Ian talked about to the proper conditions, very high in Earth's atmosphere and very fast, so that it looks like to these articles, to these technologies, that they're flying at Mars, that they have the same conditions they have there, so we test them at full scale. in those conditions to make sure that they're going to work at Mars. We want to test them here where it's cheaper before we send it to Mars to make sure that it's going to work there. Now this shakeout flight is, if I can get the first graphic here, has two stages to it. We first launch in a very large 34 million cubic foot helium balloon. That balloon carries our 7,000-pound test vehicle, which is this vehicle right here, up to 120,000 feet. From 120,000 feet, we then drop the test vehicle, and just for a few tenths of a second, and then it fires up a series of spin motors, which get the vehicle spun up to lock in its attitude, and then we fire a large Star 48 motor to accelerate it from 120,000 feet altitude up to the top of the stratosphere at 180,000 feet, and going about 4 times the speed of sound at about Mach 4. At that point, in the middle there, during the test period, we deploy the SIAD, the 6-meter SIAD around the vehicle, the inner tube that Ian talked about, and see how that behaves in the environment. And then once it slows down from Mach 3.8, where we deploy the SIAD, down to 2.5 times the speed of sound at Mach 2.5, we deploy the large parachute and see that large parachute and how it behaves. That large parachute also serves as the chute that descends the vehicle down to the surface of the ocean, where it splashes down and we recover the vehicle from the ocean. All right, so if we can take a look at this vehicle right here. This is our test vehicle. It is actually 15 feet in diameter. It flies in this direction with this heat shield forward. It has a large Star 48 rocket motor, as I said, to propel it. In the vehicle, around the side here, in this gold area, is where the SIAD is stowed. It is kept very tightly against the vehicle during its entry into Mars and its flight here on Earth. And then when it deploys, a cover comes off and it deploys out at this inner tube, which increases the size of the vehicle to 6 meters from 4.7 meters. In here, we also have this parachute can. This is where the parachute shoots out of after the SIAD has done its job. And the vehicle has a tremendous amount of instrumentation to observe the flight, to measure the characteristics. We have a camera mast here to look at the SIAD deploy, to watch the parachute deploy. We have many sensors to reconstruct the trajectory and to measure the characteristics of the inflation of the devices. This vehicle has been named here in Hawaii as Keiki o Kahonua, which is a boy from Earth. And so that's the vehicle we're going to be launching sometime in the next 2 weeks. If we can go to the first video there. So here we see the balloon launching. This was a test flight that we had out of Fort Sumner, New Mexico, of our launch tower. We have a special launch tower that we developed for this, which also was named, it's Onika Honua, which is the mover of the Earth. And this is a large balloon. Most of the helium is kept up in the top of the balloon. When it's fully inflated at altitude, the balloon would fill a large football stadium like the Rose Bowl. It's an extremely large balloon, and that's what carries the vehicle up to 120,000 feet. Here you can see it departing and flying over the surface of New Mexico. It will deploy out from here from Kauai and go straight out over the ocean, out into the middle of the ocean in the protected range that PMRF has provided us out there. And next slide. So then once we get up to 120,000 feet, we do what we call the drop. There you see the vehicle dropping from the balloon, firing its Star 48 motor, and it's pointed roughly up. It goes up and then it turns over as the motor fires, and it goes up higher and thinner in the atmosphere. It is now going roughly sideways. It spins down, and now in the video you'll see the SIAD deploy very rapidly around the vehicle, and that provides the additional drag that we're going to need at Mars to slow these vehicles down at high speed so that we can land larger payloads. If we go to the next video. The next thing that happens at Mach 2.5 is we put out what's called a balloon. This is actually a 4.4 meter device that's used to pull the parachute out. Here we see the parachute being pulled out of its can, out of the vehicle. The bridles on the vehicle stand up, which is what holds that parachute. And then the parachute deploys and slows it down. So that's what a view from the camera will look like that we're going to see of the parachute deploying into the high, thin Earth's atmosphere, simulating the Mars atmosphere. And so that's our flight. This is an experimental flight. We're testing now to see if we're able to do this. We're able to get this vehicle up to Mach 4 in the proper conditions to deploy these devices. We are in the process of building 2 more vehicles that we're going to want to fly next year. Those will be our flights of record to actually measure the performance of the SIADs and the parachute in those 2 flights in the summer of 2015. And also, I'd like to also again thank Captain Hay for hosting us here at PMRF. This is a unique facility for our mission, providing fantastic support for being able to conduct this flight. So thank you. I think we then, Dave, open it up to questions.
Okay, thanks, Mark. We will open it up for questions first here at PMRF and then over to reporters on the phone. If you're on the phone and would like to ask a question, please hit *1 and you'll be added to the Q&A queue for this briefing. For folks here in the audience, if you have a question, please wait for the mic to get to you, and if you want to raise your hands, we'll send a mic over to you.
Howdy, Andrew Pereira with KITV. You're kind of opening yourselves up to all kinds of conspiracy theories with the saucer shape. Could you tell us a little bit about the saucer shape design?
Well, this was the shape of actually our entry vehicles that we send to Mars. And so when we land something on Mars, it looks very much like this. In fact, it's the same size. We had to make it to the same scale. And I suppose it does have a little resemblance to a flying saucer, though it doesn't fly like you see in the movies. It flies this way. Now, when that picture you saw of the flight that was in 42 years ago in the summer of 1972 to practice for Viking, that flight was actually out of Roswell, New Mexico. So you decide.
But to be clear, right, aerodynamics, aerothermodynamics determine the shape more than anything. Yeah, it's physics.
Okay, do we have another question from folks here? If not, we'll go ahead and take a question from our reporter on the phone. The first one is from Alan Boyle of NBC News. Alan?
Hi, thank you for taking the question. I wanted to ask, what could go wrong, and if it goes wrong, what is it going to look like? Will you be able to recover the vehicle, go through the worst-case scenario?
Okay, so I think... Could you repeat the question, Dave? I think I heard it.
I think the question was what would... A little feedback there. If something goes wrong, what would you do, and would you be able to recover the vehicle?
Okay, so our objectives for this first flight are to launch it from here, get the balloon off and out over the water, to get it up to altitude where we can drop the vehicle, and to drop the vehicle and conduct this powered flight and get the data back from it to see how it works. As I said, this is an experimental test flight, and so we want to get that data back and see how the vehicle flies, make sure that it can get to the conditions that we want it to get to. We also want to be able to recover the balloon envelope. After that balloon has done its job, the helium is let out of the balloon and it descends into the water. Naturally, we always want to clean up our messes, and so we go out there with a recovery boat and get that plastic out of the water and bring it back for disposal. So those are the objectives. Now, what can go wrong with that? We could have a problem with the balloon on ascent. The balloon could fail on ascent. We could have a problem with getting the vehicle to operate. There are several different things that could happen there. What we want to really get, though, is the data. We want to get that balloon to altitude, drop it, and fire that motor. And if we fire that motor and we get data back from it, that is a great day. And that way we can learn exactly what happened and understand what to do for our next flights.
Okay. Again, if you have questions on the phone, please hit *1 and we'll add you to the queue. We'll now take a question from Tracy Watson of USA Today. Tracy?
Yes, thanks. Can you tell me from how far will this balloon be visible? It's a pretty big thing. And can you also talk a little bit about why the current technologies for getting things to Mars are inadequate? Why not just keep using the sky crane? Thank you.
Could you repeat the question?
What is the altitude you're going to be going to? Why are the current technologies such as the sky crane inadequate for what you're trying to do?
Okay. You want to do the first one?
And how long will it be visible for from here at PMRF or to anyone in Hawaii looking up?
How visible is the balloon?
The balloon.
Oh.
And will you be able to see the test flight?
The balloon itself will ascend the test vehicle to about 120,000 feet altitude. At that altitude, the balloon expands, and it's over 300 feet in diameter. It's quite large. In terms of visibility, that's a good question. I'm not really sure. It's going to be, sailing or floating west out over the Pacific Ocean. I'm not sure from how far you'll be able to see it.
Yeah, it'll be out there about. I'll answer a little bit. It'll be out there probably 50 or more nautical miles. I'm looking out there right now. You can't see it, but there are clouds out there. If there are clouds out there like I see now, you wouldn't be able to see it at all from distance. We'll be able to see it launch from the base here and start to ascend and leave and go out and turn into a dot. And from there, it's likely we won't be able to see it directly. But we do have cameras on the vehicle. And so we're hoping to get telemetry back from the vehicle in real time and see the operation of the vehicle in flight through the radio.
Even though the balloon is very large, it's at an altitude about 4 times higher than a typical airplane would fly. So I'm not really sure how visible it would be. The second question related to the technologies that we currently have for landing on Mars. Landing on Mars is an extremely challenging thing to do. The atmosphere is extremely thin. It's about 1% the density of the Earth atmosphere. That means that you need very large devices to react against the atmosphere, to create the drag that we use to slow the vehicles down as they enter the atmosphere. The current technologies are the ones that we've used to land things like the Curiosity rover, the Mars Science Laboratory, and the limitations are largely associated with the conditions that we can deploy those technologies, like the supersonic parachute, and the size of those technologies. If you want to land things that are even heavier than the Mars Science Laboratory, if you want to land several tons, and as you, again, cast your eyes to the horizon and you think about landing humans on the surface of Mars, missions that will be 10 to 15 tons, 20 tons or more, you're going to need extremely large drag devices to slow those vehicles down as they enter the Martian atmosphere. We don't have those currently, and that's what LDSD is developing, are the technologies and the drag devices that will allow us to slow those vehicles down safely to enable them to land on the surface of Mars.
Also, I'll add one more thing. There was a question about the sky crane. This technology is for what we call the descent phase of landing on Mars. We have entry, we have descent, and we have landing. And so, in fact, these technologies, the SIAD and the parachute, would be decelerator stages, 2 stages that would come before the last stage, which is where we use rockets to slow the thing down to the ground. And so very likely this technology would be followed by the sky crane that we used on MSL. But if we want to put down more mass, the sky crane by itself can't do that. We need these decelerators stages before the sky crane to slow it down enough so the sky crane can take over and then do its job at the very end.
Okay, thank you. Again, if you have questions on the phone, please hit *1, and we'll take one more from the phone, then we'll come back here. Mike Wall from space.com.
Yeah, thanks guys for actually doing this. I just had a quick question. There are going to be cameras on board, right? So is this all going to be webcast live, and are we going to be able to see this happening? Could you just give us a sense of like what those of us watching here at home will be able to see, and also when is this going to happen? When does the window kind of open up for launch and everything?
Okay, so we have several cameras on board. We have GoPro cameras, 4 GoPro cameras, which are used to give us real-time imagery for situational awareness. Those send data back in real time on the radio, and so we'll hopefully be able to see those during the flight and see the flight conduct and the parachute deploy, side deploy, those sorts of things. We also have several other cameras on board that are higher resolution, higher speed, that will give us much more detailed data on the operation of the devices. Their data is recorded on board, and so we will need to recover the flight image recorder, which is part of the test vehicle, in order to get that data back. In terms of when we can go, as I said, there are opportunities over the next 2 weeks. So June 3rd, 5th, 7th, 9th, 11th, and 14th are our 6 possible launch days. In the next 2 weeks, we are dependent on weather. We need to have the proper winds to take the vehicle away from Kauai and out over the ocean. And so we're watching the weather every day very carefully, and we'll pick a day that's the best day to try and launch this and get it out and conduct the mission.
In the webcast.
Actually, I don't know, maybe Dave, you can answer on the webcast.
And I was going to say, we will be webcasting live the test whatever day and time it takes place. We'll be streaming it live over the internet and carrying it as well on NASA television. We have a question from social media, I think. One up here in the front row. Microphone, please. Sorry.
Hi, one of our followers has asked, will you use a modified balloon for the actual Mars mission?
Use a modified balloon? No, the balloon that we're using here is to put our test vehicle in an altitude that will enable it to drop from the balloon and accelerate to several times the speed of sound. What we're trying to do is replicate the environment in which these technologies would be used. That means replicating the atmosphere, in particular the density of the atmosphere, which is, again, at Mars, it's extremely thin. And so to find that thinness of an atmosphere, we have to go halfway to the edge of space, or 50 kilometers, about 180,000 feet here on Earth, to test these devices, and we have to go several times the speed of sound. We will not be using the balloon to land missions on Mars. The balloon is more of a testism, if you will. It's something that we're using to test these technologies.
Okay, thank you. We'll take a question here in the back.
Hi, good morning, gentlemen. Ramsey Wharton. I'm with Hawaii News Now. My understanding, if you're looking at the largest payload, as you mentioned, about 20 to 40 tons, that's the big one. But right now, this inflatable device, which I understand is more for the robotic missions, what is the highest load that you're looking at to be able to bring down safely?
With the size of the technologies that we're testing here, we think we could double the mass that we land on Mars. So we could go something from like the 1-ton Curiosity rover to something twice that. We could also land it more accurately and to higher elevations than we've been able to reach on Mars. But the technologies we also think are very extensible to those mass ranges that you discussed, the 20 to 30 tons. That is, for example, the parachute. You know, the way that we use parachutes here on Earth when we return, say, the Apollo command module or the Orion crew capsule is we use them in clusters. We use several parachutes to generate even more drag. Even though we're only testing one parachute in the next few weeks, we think that the parachute we're developing and testing is amenable to being used in clusters. Several parachutes at once to produce even more drag. And those kinds of things are the technologies that would enable the 20 to 30 tons that we're talking about.
Also, and just before, so that's why we want to be good guests with our hosts, because we think we'll be back.
Yeah.
And also just a quick, if you have the mic here. Yeah, a quick add-on to that. We need to get to 20 to 40 tons to put people on Mars, but we can't do that in one step. We have to take a kind of a step at a time. And so we did 1 ton, and we're going forward with the technology development to go up to twice that, and we'll take a few more steps over the next decades to lead up to the ability to land people on Mars. And that's the great thing about having the Space Technology Mission Directorate is it can fund these things well in advance of the mission, so we can reduce the risk of actually trying to do those missions when we have to go do them, get confidence in the technologies, know how we're going to do it, what it's going to take to do it, and then we can step in and build them and do it.
Can you hear me? There we go. Summertime, if all goes well now, you're looking at expanding that inflatable to the 26-foot size diameter, is that right? This is the one for the larger load.
The first one we're testing is 6 meters in diameter. It expands off the periphery of the vehicle. That one's about 20 feet in diameter. We hope to come back next year and test one that's 8 meters, which is even larger. And that would, again, enable even more mass to be landed on the surface of Mars. You can grow those even further. We're not really sure what the limits are. You know, it's one of the reasons why we're doing some of this testing. But the parachute, you know, the 30.5 meter or 100-foot diameter parachute is also something that would be used in those missions.
Okay, and again, if you have questions on the phone, please hit *1. We do have another question on the phone from Sarah Diener of AOPA. Sarah?
Hi, thanks. The 8-meter model, will that be a different design or just a scaled-up version of the 6-meter model?
The 8-meter side that we'd be testing is a very different design, actually. When we started thinking about what it meant to deploy inflatable decelerators, the first steps that we started taking were how do we develop this technology, and how do we develop in a way that we're familiar with? How do we test it? How do we know how it performs? And one of the key elements of that is making a device that acts as if it were a rigid device. We fly rigid structures to Mars routinely, and we know how they perform. We can scale them to very small sizes, you know, things that are even smaller than this, and put them in a wind tunnel, for example, and test the aerodynamics and feel comfortable that the aerodynamics that we're seeing are going to be extensible or extractable to models or to vehicles that are several times the size that we're testing. We wanted to do a similar approach with the inflatable decelerators. So the 6-meter is really designed to be something that acts as if it were a rigid structure. The 8-meter device is something very different. As you start developing these inflatable decelerators, you're going to have to wrestle with what it means to have these very flexible structures that are attached, you know, directly to the front of the vehicle. And the 8-meter starts moving us in the direction. Instead of it being a higher pressure device, it's something that is much lower pressure. It's actually ram air inflated using the oncoming supersonic flow to inflate the device, but it also has much more flexibility associated with it. the aerodynamics of the device determine the shape that it takes and vice versa, and the shape determines the aerodynamics. And so in that regard, the 8-meter device is really our first foray into understanding what it means to have very large devices that are flexible, that will interact with the oncoming flow, and whose shape may not be determined a priori. And it's that excitement that means what is it, how do we develop these technologies and what are the behaviors of them? As we move to larger and larger devices, these are questions that we're going to have to answer.
Okay, thank you. We'll take another caller from on the phone, Tracy Watson of USA Today. Tracy?
Can you talk about what the inflatable portion is made out of and how big it gets when it deflates compared to how big it is when it's stowed? Thank you.
The test vehicle is 4.7 meters in diameter, about 15 feet, and it's essentially a full-scale replica of what a Mars entry vehicle would look like. When we inflate the SIAD, the first SIAD that we're testing is a 6-meter device. So we go from about a 4.7 meter to a 6-meter device. And that, again, would enable us to, in conjunction with a parachute, to almost double the mass that we can land on the surface of Mars. The materials that the SIAD are made out of, we actually use Kevlar, very similar to the Kevlar that's used to build bulletproof vests. But we also apply some coatings to it to allow it to withstand some of the temperatures that you would see as this thing is inflated and deployed at several times the speed of sound. So we're talking temperatures upwards of 600 degrees Fahrenheit. To survive those, not only do you have the Kevlar, you also have some coating associated with it that will allow it to absorb some of the heat and the energy of that high supersonic flow.
Okay, again, if you have any questions on the phone, please hit *1. We'll come back here and see if there are any more here. Having no takers here. Oh, wait, we do have one. Sir.
Andrew Pereira again with KITV4 News. Is there any earthbound uses for the technology that you're testing today?
Absolutely. Aerodynamic decelerators are devices that can be used anywhere where there's an atmosphere. That can be Earth, that can be Mars, that can be Titan, that can be a number of bodies in the solar system. The Earth atmosphere is nice in that it's very thick, and so needing to deploy these devices at supersonic conditions is not a problem that we routinely face, but certainly there's applications where these devices would have a role here at Earth.
Okay, any other questions from here in the audience at PMRF? All right, with no further questions, we'll go ahead and wrap up today's briefing. Thank you all for joining us on NASA television and here in person at the Pacific Missile Range Facility on Kauai, Hawaii. Stay tuned. We'll be updating the potential for a launch tomorrow through our social media websites, our mission website, as well as media advisories. You can follow along with us and find out the latest on the launch date and time by following @NASA_technology or @NASA. We'll also be posting updates to the LDST mission page on the web, which is linked from the space technology page on www.nasa.gov. Thank you all for coming.